Good afternoon. Thanks to everyone present in Google Meet and YouTube for following this seminar today. And today we have the honor of having Professor Moira Mary Jardine from University of St. Andrews in UK. Moira, thank you for kindly accepting this invitation. And let me tell you a little bit about Professor Moira. She worked at the University of Sussex, and since '96, she works at the University of St. Andrews, where she also got her PhD back in '89. For her outreach work with young people in local schools, she was awarded the Young Persons Award in 2002 from the Royal Society of Edinburgh, and she was promoted to personal chair in 2012 and became the first female professor of physics at the University of St. Andrews. And in 2013, she was elected a fellow of the Royal Society of Edinburgh. Professor Moira has broad research interests in the area of young stars, particularly the structure of their magnetic fields, and coronae, and the mechanisms by which they interact with their disks. And today she's going to present her research on prominences as tracers of coronal structure and mass loss in cool stars. So the questions will be directed to Moira after her presentation. And if you are following the seminar via YouTube, you can please indicate in the chat that you have the question that I'll bring it to Moira. And if you are in Google Meet, just push the button, raise the hand. And before the seminar starts, I would like to ask everyone to please turn off your microphones and cameras. And Professor Moira, you can start whenever you want.
Okay, so let me just get my talk to display to you. This is always a nervous moment for any person giving a talk, and we have to make sure that the technology all works. But I'll assume if I don't hear anything from you that you can now see my presentation.
It's perfect.
Thank you. So today I'm going to talk to you about stellar prominences and how they can be used to trace the structure of coronae in young stars and also their mass loss. And I have a little cartoon here of what I mean by a stellar prominence. So here is the star with its magnetic field lines in black, and this feature here is cool coronal gas that has condensed and is trapped on the field lines. So it's acting a little bit like iron filings in outlining the shape of the magnetic field. But I want to start my talk with a bit of an introduction. So before I talk about other stars, I want to talk a little bit about what we know about the sun and the structure of its corona. So here I have a beautiful eclipse image of the sun. And so what you're seeing is the moon has passed in front of the sun, and we're seeing the structure of the sun's corona. The coronal gas is at millions of degrees. It's extremely hot. And you see two different types of coronal structure. There are these very long, almost straight, almost radial features. And this is where the hot coronal gas has stretched out the magnetic field lines of the sun. And so this is outlining the structure of these magnetic field lines. And this is where the gas is escaping from the sun's corona. It's so hot that it's evaporating away from the star. But we also see these structures here, which are like loops. You see them more clearly on the right-hand side. And these are closed magnetic field lines that are enclosing the hot coronal gas. So we see both of these types of field lines, the field lines that contain the gas, and these ones here where gas is escaping in a wind. Now we have the great success really in looking at the sun. We can directly image the sun, and we know that the sun doesn't stay the same forever. So the sun has a magnetic cycle. So over a period of about 11 years, as it shows in this graph here, the number of sunspots, that's what's plotted, rises and falls on a time scale of about 11 years. And this is the time scale in which the sun's magnetic field changes. So if we were to look at the sun on a timescale of about 11 years, we would see the magnetic field growing and decaying in strength. But it's not just the amount of magnetic field that is produced that changes with time, but also its structure. So if we look at the images on the left, the top left is showing an eclipse image of the sun at the minimum of the sun's magnetic cycle. So you can see there's lots of emission around the equatorial regions here. And that's because the emission is coming from the active latitudes, the latitudes of the sun where we see most of the spots. These dark regions at the poles are where the wind is escaping. If we look at the maximum of the cycle, when there are most spots on the surface, we see a very different picture. There is lots of bright emission at a whole range of latitudes. And that's because there are more spots and they're at a greater range of latitudes. But it's not just the structure of the sun's magnetic field that changes over the course of the solar cycle. The mass loss from the sun changes also. And we can see this in the images on the right. So these are both composite images. So there's an X-ray image, that's the color image here. You see lots of bright emission from the equatorial regions at cycle minimum. But there are also contours of the speed of the solar wind. So these are measurements made by in situ spacecraft. So the two contours are, the inner one is a speed of about 300 kilometers per second, and the outer one is about twice that. So you see that over these regions that are dark in X-rays, we see this fast outflow, the fast solar wind, and over the active regions, we see this much slower outflow. And strangely enough, that's called the slow solar wind. The panel on the right, however, is taken at cycle maximum. So we see emission at a much greater range of latitudes than the sun, but we also see that the wind speeds are much more variable. You see very high wind speeds at some locations, very low wind speeds at others. So it's a much more complex picture that we see at cycle maximum. So from the sun, we learn that as a star's magnetic field changes, not only the distribution of X-ray bright regions in its corona changes, but also its wind will change. So this is what we know about the sun today. Now the sun is a fairly middle-aged star. It's reasonably inactive. But we expect that when the sun was much younger, that it was much more active. We can estimate this by predicting or modeling how the rotation rate of the sun has changed with time. So this is a plot of the angular velocity of a star in units of the angular velocity of the sun as a function of age. And you notice the age is in units of millions of years. There are three curves plotted here. So these are rotational evolution curves for three different stars. One that began its life spinning slowly, an intermediate rotator, and a rapid rotator. But all three curves show a very characteristic shape. In the very early years, the first 10 million years in the life of a star, the star is still surrounded by a protoplanetary disk. And the magnetic field of the star linking into this large disk keeps the rotation rate of the star constant. So we have a flat line here. But the disk doesn't live forever. Some of the material forms into planets, some of it accretes to form the star, some of it is lost. Once the the disk around the star is lost, the star will spin up. And that's because the star is still young, it's still contracting, and so to conserve its angular momentum, it must spin up. But eventually, the star reaches the main sequence, its radius is no longer changing, it's no longer contracting. But at this point, it is still generating quite a strong magnetic field through its internal dynamo. And this powers a wind, just like the wind we saw from the sun. This wind carries away not only mass, but angular momentum. And so we see the angular velocity of the star decreasing as its wind carries away some angular momentum and spins the star down. Now, we can look at many different open clusters. So here's H Persei here, and plot all the rotation rates of all the stars in that cluster. And this gives us some indication that we can use to constrain these models. But the problem we have is that it's almost impossible to observe these winds directly. We observe the rotation rates of stars, and from that we infer that they've spun down, so they must have lost angular momentum. But we don't directly observe the winds that are doing this. On massive stars, it's much more straightforward to observe the winds which are more massive. But the winds of solar light stars are very difficult to observe. So this is one of the challenges that we have to understand the rotational evolution of stars when we can't see their winds. So what sort of magnetic fields do we think are present on all these stars? And here are just 4 different examples that I have for you. Here's Epsilon Eridani, which is a very well-known star. What you see plotted is a map of the radial component of the magnetic field at its surface. And the colors here are denoting the intensity of the magnetic field. And you see it's around 1020 Gauss. So this looks like just a tilted dipole, a very simple field. AD Leo has a surface magnetic field that's almost a pure dipole. And these 2 stars on the bottom are very famous planet-hosting stars. We've got HD 189733 and Tau Boo. And they show a more complex distribution of field at their surface. So how do we produce these maps of magnetic fields at stellar surfaces? Stars are just point masses. We don't typically resolve the surfaces. So how do we learn this? Well, we use the Semen effect. You know that in the presence of a magnetic field, spectral lines can be split, and the amount of splitting depends on the strength of the magnetic field. The 2 components into which the lines are split are polarized in a different way. So if we take the difference between the left circularly polarized and the right circularly polarized component, we have something that's called Stokes V signature. So if we can observe the Stokes V signature as a star rotates, we can learn about the line of sight magnetic field. So I have a little illustration of this on the right. So the red patch on the star is a patch of radial magnetic field. And underneath is a plot of the Stokes V signature. And we can see it changing with time. So when the patch of radial magnetic field is at the very center, about now, the Stokes signature has its largest amplitude, and it's 0 when the patch of radial field is at the limb, because then there's no line of sight component. I should say that we can only detect the largest scale field with this technique, because if you have small regions of mixed magnetic polarity, they cancel out. I could do the same thing with a patch of azimuthal field at the surface of the star. In this case, the maximum amplitude of the Stokes V signature is when the field is at the limb of the star, and then the field lines are pointing towards you, and it's 0 at the center. And you note that the signature changes polarity as the patch of magnetic field goes from the approaching limb to the receding limb. So by tracking how the Stokes signature changes in time, we can infer the structure of the magnetic field. So this is the sort of data that we might get. This is a set of dynamic spectra. This is velocity on this axis. It could also be wavelength. And this is the rotation phase of the star, or equally time, running up this axis. And we can see the Stokes signatures moving through the line here. So we typically express the magnetic field in terms of spherical harmonics. So Br, B theta, B phi are written as a sum of spherical harmonics. And the parameters that we actually fit to the Stokes profiles are these coefficients, alpha, beta, and gamma. So these three coefficients are iterated until we achieve the best fit to the observations. So we can also express the field as just the alpha and beta terms. These are the poloidal components of the field. And I've drawn a very simple axisymmetric field here and outlined the poloidal parts in red. And these terms describe the toroidal parts, which for an axisymmetric system, you could think of as being the azimuthal component of the field. So what do these field structures look like? We only observe the magnetic field at the surface of the star. If we want to learn what the magnetic field is like in the whole corona, we have to extrapolate the field out from the surface. And of course, there are many ways of doing this. So here's one star, GJ49. And on the left, this is a potential field extrapolation. Now, a potential field is the lowest energy state for a magnetic field, 0 volume currents in the corona. And here I've drawn the closed magnetic field lines in white, and the open ones are carrying the wind in blue. But on the right is a non-potential field fitted to the same data. So a non-potential field has currents in the corona. So the field is stressed above its lowest energy state. Both of these solutions were made from the same magnetogram, but the coronal structure is quite different. So how do we test our models of the coronal structures of stars? We need something that traces out the structure of the magnetic field lines in the corona. So this is where I have a little pause to give you a culturally appropriate analogy. So this is some images of a Scottish sport. It's called throwing the hammer. And the hammer is this thing here. It's a ball of metal, very heavy metal, on a long chain. And so what you do, what this gentleman in yellow is doing, is you spin around and you swing the hammer around your head very, very fast, and then you let go. And the trick is to get it to travel as far as possible. So this is a metaphor, if you like, for our prominences. So the man is the star spinning around, the chain is the magnetic field, and this iron ball is the prominence. So the magnetic field is containing the prominence. If the magnetic field releases the mass, it will fly away from the star. And hence the little cartoon that I have drawn here. So for the rest of my talk, I'm going to tell you about how we can use these prominences to measure the stellar winds that are otherwise so difficult to observe, and to trace out the structure of the star's magnetic field. So here's how we observe these slingshot prominences. Here's a rotating star and a prominence in its corona. And underneath here is the H alpha line. Now, these stars are very active, so H alpha is filled in almost to continuum. So I've drawn the line as almost flat. This limb of the star is approaching us, is coming towards us. All the photons from this limb of the star are blue shifted. They would appear out in this part of the line. So when the prominence moves in front of this limb of the star, it scatters these photons out of the line of sight, and we see a little absorption dip. As the prominence moves from left to right, this absorption dip moves from the blue part of the line round to the red part of the line. So if we observed the star many times and stacked these spectra up in time, we would see an absorption dip moving from the blue to the red through the line. The time it takes for a feature to move through the line tells us the time over which the prominence transited in front of the star, and that tells us the radial distance of the prominence from the rotation axis. So here's what we actually observe. This is a star known as Biomic because it's a very rapid rotator. Its correct name is Biomic. And what we're seeing are two sets of observations taken on 2 consecutive nights. So this is time on this axis, and this is velocity. And you see there are many of these dark stripes moving through the H-alpha line. And as a guide to the eye, we've drawn a line through each of them. Now, if we look one night later, you see that this feature here, which is marked A, is still present, but this feature marked B has disappeared. So this absorbing feature over a time scale of 24 hours disappeared. Many of these features are still present one night later. Some of them have changed. This feature here appears to have weakened. So what we take from this is that on a timescale of a day, the distribution of prominences must be evolving, but the overall pattern is similar. There are a similar number of prominences from night to night, but clearly a timescale of about a day for their lifetime is not so far wrong. So let's look at another system. This is a very young star. So it's this TWA6. It's only 8 million years old. It's rapidly rotating, about half a day. And it's at a very critical stage of its evolution, just at the boundary between being fully convective, as it was when it was younger, and it's just about to develop a radiative core. I'm showing you 2 plots on the right here. The first one is a plot of the spots on its surface. And this is a projection where you, the observer, are looking down on the rotation axis. So this solid line here is the equator, and this is latitude 30, and this dotted line is latitude 60. These little tick marks mark the rotation phases at which observations were acquired. Now, what you see is that there are lots of spots on this star. It's a very heavily spotted, very active star. It's got spots at its rotation pole, which is something the sun never does, but it's very typical of active stars to do this. And on the right here, we see the H-alpha traces. You can see the prominences moving through the line. So from the H-alpha traces, we deduce that there is at least 1 prominence present, and it's out at 4 stellar radii. That's a long way out to be supporting a prominence. Now, thankfully, it's inside the prediction that we made for the maximum height at which you can support any prominences. So it's a well-behaved prominence. It gives you some idea of the scale of these features that they form so far out from the surface of the star. Here's another example. This is another pre-main sequence star, slightly older, just 15 million years, called LQ Loop. Again, very rapidly rotating. Now, for those of you who can do coordinate transformations in your head, this is actually a plot in velocity space. This is a back projection for the experts. So this is the x velocity and the y velocity plotted. The color is showing you the locations of the prominences. And the white disk in the center is the disk of the star. What you see is that all of the absorption clusters around this red dotted line. And this is very characteristic of these slingshot prominences because they typically form at or just beyond what's known as the co-rotation radius. And this is just the radius at which the inward pull of gravity is exactly balanced by the outward centrifugal forces. So you can think of it as like a gravitational potential minimum. And this is always where we see prominences forming. If we look at the observations taken 4 days later, you see that the distribution of prominences has changed slightly. So this new feature here has grown. But again, they're forming at or just beyond the co-rotation radius. So here's my last example for you. This is a particularly nice example because the spots and the magnetic field and the prominence locations were all mapped simultaneously. So all the observations were made at the same time. So this is V5.
Excuse me, Moira.
Yeah.
Sorry. I think the slides are, it's stopped in slide 15. Maybe it will be necessary to stop sharing and to share again.
Okay, let me just do that. Yes, if you've lost track of the slides, then we absolutely need to try that. Let me just find the window again. So I will stop presenting, and you can. So that should have stopped. So let me try presenting again. Maybe just the link was lost.
Yes.
For a moment. Yeah. Thank you for pointing that out to me. So let's just see. So is this showing now?
Yes.
It's gone back to the start, but that's okay. I'll just flick through. Should probably confuse it terribly, but never mind. Can you see slide 17 now?
Yes. Yeah, perfect.
Excellent.
No, thanks.
Thank you very much. Okay, so here we are. V530 Power. This is it's also known as AP149. So for the experts on the left here, I have some evolutionary tracks. So the black lines are the evolutionary tracks for stars of different masses. And you see the star evolving through this parameter plane, which is luminosity against effective temperature. The blue dashed lines are equal age lines. And these are two possible solutions for this particular star. So this suggests that it's about the same mass as the sun, and it's come down off its Hayashi track, and it's on its Henry track approaching the main sequence. And on the right-hand side, we see the surface magnetic field plotted and a field extrapolation. So here are some H-alpha traces on the left here, showing the existence of some prominences around this star. And on the right, these are plots in velocity space again of the locations of the prominences. And again, the black dashed line is the co-rotation radius, and you see the prominence material clustering around the co-rotation radius. When we look a few nights later, the distribution has changed slightly, but the overall pattern is the same. So just to summarize, we see these features in many types of rapid rotators, from active G and K stars through M dwarfs, very low mass stars, and in pre-main sequence stars. But the common theme is that these stars are all rapid rotators. Now, up to this point, I've only talked about material that is trapped in the coronae of stars. But we also see material ejected from stars. So this is a low mass star, V374 Peg. It's about a third of a solar mass. And what you see in this plot is, again, the H-alpha line. Here you see it here. And we see two different things here. We see prominences. Now, this is just one of those things. The color table in this plot is inverted from all the other ones I've shown. So here, the lighter shades here are actually absorption. So there's a huge prominence structure here and another large prominence structure here. So within the line profile, we see absorption. So that's within a V sin I of about 36 kilometers a second. But we also see absorption features way out at much larger wavelengths, way out in the blue wing of H-alpha. So these correspond to larger velocities, about 675 kilometers a second. And these three features that are marked are these three ejection features that we see. Now, interestingly, the authors of this paper noted that there were surprisingly few mass ejections given how many flares are seen in this star. And I'll come back to that in a moment or two. But I wanted to show this to show that some of the material is confined with the star and rotates with the star, but we also occasionally see ejections. Now, the group that did this, Christian Vida and his collaborators, then went on to look for these, they're called coronal mass ejections, in lots of stars. So they surveyed about 25 M dwarfs, and they looked for asymmetries in the H-alpha lines. So what you're seeing on the right here is a summary of their results. And the top left is a histogram of all the blue shifted features that they found. And below that is a histogram of all the red shifted features. And on the right are the masses that they deduced from this. Now, interestingly, the peak of these distributions is below the surface escape speed. So Vida et al. Concluded from this that they were observing lots of motions, but not all of them were material being ejected. They simply weren't fast enough to reach the escape speed for the star. There was a further study done by Leitzinger et al. in 2020 of slightly more massive stars. So these were F decay stars. They didn't manage to observe any coronal mass ejections, but they did suggest that this was because their observing times were actually too short to see these features. So let's go back to comparing this now with what we know about the sun. We know that we observe features that look like mass ejections from other stars. So where do these lie in relation to solar mass ejections? So if we look at this plot here, it's a plot of the kinetic energy in coronal mass ejections as a function of the X-ray energy of the associated flare. So often when you have a flare, there's mass ejected at the same time. And this is a plot of the energy in the coronal mass ejection relative to the energy in the flare. And all the red triangles are observations of the sun. So these are individual flares on the sun. And this plot was originally made by Jeremy Drake and his colleagues in 2013. So they put all the solar plots on the one graph, and then they made the point that if you extrapolate this to the typical X-ray energies that we see from stellar flares, then the predicted energies in the coronal mass ejections would be enormous. It's some ridiculous factor, like 1/10 of the bolometric luminosity of the star, something like that. So they postulated that this relationship, which is a very nice straight line relationship for the sun, must not hold for other stars. Since then, there's been a lot of work, both in trying to model this, but also trying to observe CMEs and other stars. And you can see all the other data points here. And they do lie below this green line. So there's an indication that on other stars that the coronal mass ejections are not as energetic as we might have predicted if we had only looked at the sun. So how do we test these models? We now have puzzles about mass ejected from stars and also the structure of stellar coronae. But we can use these observations of prominences to learn about both these things. So we can take the surface magnetograms shown here, can extrapolate the field. And then within this extrapolated magnetic field, we can look for locations of stable mechanical equilibria. So locations where material could collect and be in a stable location. And that's what's shown here on the right. These are all the places where material could collect. And you see there are quite a lot of them. They land in two main clumps. And they essentially trace the structure of the magnetic field. So here's here's a model now of one particular very famous star. This was the first star on which these slingshot prominences were observed. It's called AB Doradus. So what we have is the stellar magnetogram painted onto the stellar surface here, the extrapolated magnetic field lines, and these red blobs are the predicted locations where material could be supported by the magnetic field.
Excuse me, Moira.
Have you lost me again?
Sorry. Yes, I see the slide 21 now.
You're on 21. Okay, let me see. I'm on 23. Let me just do the same again. I'll just reinitiate.
Yeah, thanks. Sorry for
That's okay.
the problem.
I'll just give it a moment and try again. Okay, so let's try sharing again. Okay, so let me go back to where I was. Can you see that now? It's a movie that's playing.
Yes, it's fine.
Excellent.
Thanks.
Thank you. Okay, so on the right-hand side, you see what you would have observed if you'd been at the telescope. As a function of time, the H-alpha dynamic spectrum is filling in, and you see the absorption transients that are moving through the line as the prominences pass in front of the star. So as the cool material transits in front of the star, it blocks out some of the stellar light, and we see these absorption features moving through the line. So this is the model based on the observed magnetic field at the surface of the star. So how does this compare with what we actually observed? So here's the comparison. On the left are the synthetic H-alpha spectra, and on the right is what was observed at the telescope at the same time. And you see that the main features reproduce quite well. There are two clumps of absorption here and here, and these are reproduced quite well here and here. So this gives us some hope that we can use the observed prominence absorption features to test our field extrapolation, because the material is trapped on the field lines, so it's outlining the shape of the field. So here is a comparison. On the left is a potential field extrapolation. So as I said, this is a magnetic field that's in its lowest energy state. And you can see the red blobs here trapped on the field lines. These are the predicted prominences. And on the right is a different model, a model where the magnetic field is not in its lowest energy state, it's stressed. And you see the field line structure is very different and the prominence locations are very different. These are the synthetic H-alpha spectra produced by each model. On the left, the potential field, and on the right is the non-potential field. And you can see that they're quite different. The potential field extrapolation reproduces quite well both these features in the observed spectra. It doesn't get this one, it's not perfect. But the slope of these features for the non-potential field extrapolation is quite different. So prominences can be used to learn about the structure of stellar magnetic fields. What about the winds? That was the other puzzle that we had. So this is quite a busy plot, so I'll take my time with it. This is mass loss per unit surface area from the star in units of the solar mass loss rate, plotted against X-ray flux. And there are two different types of symbol shown here. So the purple squares, like these are observations. I said it was very difficult to observe the winds of these stars, but there is a very novel technique that can be used in a few cases. So we have some observations. And the purple dashed line is the fit through the observations. The circles are models based on these surface magnetograms acquired through Semen Doppler imaging. So each circle is a different star. And the colors of the circles tell you the mass of the star. So dark blue is more than a solar mass, and the yellow is a very, very low mass star. The black dashed line is the fit through the models. Now you see that the two dashed lines agree very well. So the models fit very well to the observations. But there is something that's slightly puzzling about this plot, and it's these stars here. These are all very low mass stars. They're yellow, so they're much less than 1 solar mass. And they've got very, very high mass loss rates, very high X-ray fluxes. But you notice there are no purple squares in this part of the plot, so there are no direct observations to test the model in this part of parameter space. And this is where the prominences come in again. So we can use prominences as measurements of the stellar wind. And we do this by thinking about how the prominences form. So this is a model. It's a view of the star looking down on the rotation axis. So the orange circle is the star. This dashed line is the co-rotation radius. And this flux tube here is a flux tube that has been cooled and allowed to settle into an equilibrium state. It's actually embedded in a background dipole magnetic field, but that isn't shown here. The color shows density relative to the surface density. So you can see all of the mass is collecting in the top of this flux tube. But this mass must have got here somehow. It's come from the surface of the star, and it flows up the legs of the loop to form the prominence. But the interesting thing is that the coronae of these stars are so hot that this upflow is supersonic long before it gets out to this distance. Because the upflow is supersonic, the surface never realizes that a prominence has formed. It will just keep supplying a wind. Now we can calculate the maximum mass that the magnetic field can support. This is shown here. It's just the ratio of the magnetic to the gravitational energy modified by the position of the co-rotation radius. Once the mass in the prominence exceeds this maximum, it can no longer be supported and it will be centrifugally ejected. But the surface is not aware of this, and it will just keep supplying mass. So the formation of prominences becomes a cycle of formation and ejection. And indeed, most of the very active stars fall into this category. They lie in this limit cycle regime. So we can observe the masses and the lifetimes of our prominences, and that gives us the mass flow rate of material into the prominence. It's just kilograms per second. And that must be some fraction of the mass flow rate in the stellar wind. And that fraction is just a fraction of the surface of the star that's supplying the prominence. So by measuring the masses and lifetimes of prominences, we can estimate the mass flow rate in the stellar wind, even although we can't observe the wind directly. So here is now our plot of mass loss per unit surface area as a function of X-ray flux. And these blue points are the measurements that we get from observing prominences. And you see that they fill in this part of parameter space where we had no previous observations. And in fact, they lie beautifully on the same lines. Here I've just done the same plot again, but I've overplotted the tracks of various different models of stellar winds. And you can see that the prominence observations fall well within the predicted values that we get from both from previous measurements and also from different types of models. So I've told you about prominences, and I've mentioned that we see them in very active stars. So it's fair to ask, over what fraction of the life of a star can we use prominences to learn about the winds and their coronal structure? So this is a plot of prominence mass in grams against age in millions of years. And these are the theoretical predictions of prominence masses based on a rotational evolution model, both for a moderately rotating star and a fast rotating star. The colors show you the age range over which we can expect prominences to form. The symbols that are overplotted are observations of individual stars. And you see that the observations lie quite well within the models. So this is quite nice. We have some hope that what we measure observationally and what we predict from theory are sort of agreeing. But how does the mass that is finally ejected in these prominences relate to the coronal mass ejections that I talked about earlier? Well, here is almost my last plot. This is a plot of mass loss rate in units of the solar mass loss rate as a function of time. And it's mass loss rates due to two different processes. So these are models. The red dashed curve is the mass loss rate in the solar wind as a function of time. And here we have the present day, and here are the present day observations of the solar mass loss rate today. The blue curves are predicted mass loss rates in coronal mass ejections, two different types of model, and this bar here is showing the range of observed mass loss rates in solar CMEs. And you see that although the sun has got a fairly low mass loss rate today, if we look at earlier ages when the sun was younger, its mass loss rates were much higher. Now we could add the prominences to this plot, and I did this in a very sophisticated way. I literally cut and pasted a diagram in here. So this is the mass loss rate in prominences. And you see that for a solar mass star, it's much less than you get in coronal mass ejections, but it follows the same sort of curve. It's large at young ages and it decreases as the star gets older. These are predictions for a solar mass star, but we could have done this for a much lower mass star, for M dwarfs, for example. And we can anticipate perhaps that they would have had much larger mass loss rates. So I see that my time has almost passed. So I'm going to leave you with my summary here of the very many ways in which we can use slingshot prominences. We can use them as windometers, as a way of predicting wind mass loss rates, and this allows us to measure the mass loss rates of stars in a region of parameter space where other methods fail. But we can also use them as a way of tracing out the geometry of coronal magnetic fields. So we observe the surface magnetograms using Semen Doppler imaging, we predict the H-alpha dynamic spectra, and we compare it with what is observed. And by iterating, we can then hopefully learn about the structure of the magnetic field. So at this point, I'm going to stop sharing my screen so that I can take some questions. So I will hopefully switch myself off at this point. There we are. I hope I've switched off.
Yes, thank you, Moira. I think it was very comprehensible, very complex subject, but it was very comprehensible talk. So many thanks. Let's start the questions. I will put my question first if nobody opposes it. I have, let me start. When you showed in the beginning, that's from the observations, I think from the Semen effect, so you can reduce the magnetic field or with assumption of a potential or non-potential field. In each case, the solution is unique, or you have more parameters, maybe the complexity you choose, or how is?
So if you use a potential field, then you get a unique solution with only two boundary conditions. One is the radial component of the magnetic field at the surface, and the other is the location of it's called the source surface, the radius at which all the field lines are open. So with a potential field, you get a unique solution. With a non-potential field, the solution is no longer unique because you have the other components of the magnetic field at the surface that you could vary. So there are many types of non-potential field that you could fit to the surface magnetograms. And so our hope is that you could use the observations of the prominences perhaps to understand how non-potential the magnetic field might be.
Right. Thanks. I have another question. I think you showed how to use the prominences to estimate the mass ejected, and also how to link this to the coronal, to the mass of the coronal mass ejections. But before this new technique, I think you showed in slide 21 some measurements of the kinetic energy of the mass ejected against the X-ray flux, I think. And I was wondering, how is it to estimate or to measure the mass? I think it must not be easy to estimate the mass to get the kinetic energy. Is it possible to use the variation, the spin of the star, or something like this?
So it is a difficult calculation to do. It's typically done in a few different types of ways. The best way is to use line ratios. So you observe, say, in the calcium 2 line as well as in H alpha, and you use the observations in the different lines to constrain the column density of material that's absorbing, and from that you infer the mass. But it is a difficult calculation to do, and it's not possible for every single prominence observation. So that's why there are very few points on that graph for other stars. It's something that I would hope we can improve on, but I think there's probably room for quite large error bars on that one.
Right. Yes. But is it not possible to perceive the variation in the rotation frequency of the star? I think it's too small, right, for the amount of mass that is launched to perceive any variation in the rotation of the star for one event.
Like you're thinking of with exoplanets, the Doppler wobble? Is that what you're thinking of?
Yes, because as it launched some angular momentum, it should reduce a little bit the rotation. But I think it must be so small that it's not possible, right?
Yes, I think, yes, in principle, you could do that, but I think the effect is probably so small that it would be very, very difficult. Yeah.
Thanks. I'll pass now to Maria. Please, Maria, go ahead.
Yes, thank you very much for your presentation. I have a very basic question because I'm not really into the field. I am just curious about you showed the X-ray flux plotted against the mass loss rate, right? This X-ray flux is coming from the prominence itself? No,
it's the overall X-ray flux of the star.
Okay, and you expect this to come especially from the hot places of the corona, yes, in general?
Yes.
Okay, and then which facilities you normally use for measuring this X-ray fluxes?
I guess, I mean, these measurements have been taken over many years. So many of them will be archival. So some of them might be very old. So they might be old measurements. Many of them will be XMM. So it's probably quite a heterogeneous sample. They're not all made with the same instrument.
Okay, and usually this is a soft X-ray.
Yes. Well, yes. I think most of these will be coming from, less than 10 keV electrons.
Okay. Okay, and I have another question also out of curiosity, because at the beginning you showed these very beautiful plots of the, well, infer magnetic field in the surface of the stars. And I wonder, in a non-fast rotating star, how much time would you take to make such a map, let's say?
So if the star is rotating very slowly, then there is a problem, because the lines are rotationally broadened. So if the star is rotating slowly, the lines are narrow. Mm-hmm. So it's very difficult to see the features traveling through the lines, because the lines are too narrow. In addition, a star that's rotating very slowly is probably magnetically very inactive, so it doesn't produce much magnetic field anyway. So it's a mixture of several different things. The Stokes signature will be weak. It's difficult to detect it in the narrower lines. And if you, in very inactive stars, you probably only have a few regions of spots across the surface of the star. So yeah, it's not just a matter of looking longer.
Okay, you have to be very.
you need more flux, basically.
Yeah, you have to be picky with your objects, actually.
Yes, so it's quite a highly selected sample. You have to have rapid rotators. Yeah.
Okay. Okay, thank you very much.
I have one more question.
Yes.
About these models, because you showed some models with the presence of the material ejected, how they are, how is the configuration of this material and of the fields of the star, and how to synthesize this H-alpha emission periodograms. And I would like to know, these models, you have to perform a full emitted simulation involving all the equations, or it's already somehow constrained by the observations, and it's not really necessary to solve all the equations.
So it is possible to do a full MHD simulation using the surface magnetic field as an input. And of course, our colleague Eleni Vidotto does this. And you have to use one of these enormous codes to do that. What I showed is much simpler. So these field extrapolations are very fast to do, but they assume that the field is rigid. So the field is not deformed by the material that is loaded onto the field lines. So once I solve for the structure of the field, I simply solve hydrostatic balance along each field line to determine where material will collect. And that's computationally, that's much, much faster than a full MHD simulation.
Right, and it has a lot of less parameters, free parameters, right? It's much more constrained.
Yeah, there's only one free parameter for the magnetic field, and there's only one free parameter for the density structure. So it's simple and fast, but what it doesn't give you is it doesn't give you the full feedback of the material on the structure of the field. So you need a big MHD code for that.
Right. That's fascinating. No. Okay, so if there are more questions.
I think Vera has a question.
Maria?
No, Vera.
Maybe. Vera? Let me see if Vera is around.
She's put her hand down again, so maybe she didn't have a question.
Okay. Could you? I'm not very aware about how these Xray flares are produced from the shocks that are produced for the material that's colliding already when they are launched, and when they collide with each other and heat, or how is this X-ray produced during these events?
So the overall X-ray emission of the star is just thermal emission. So the gas is heated, and there are several competing theories about how to heat gas. The one that I favor is magnetic reconnection. So by reconnecting the magnetic field, you release some of the magnetic energy to provide thermal energy for the gas. So that's just background thermal emission from a 1,000,000-degree plasma. When you have a large flare or when material is ejected, that's it's a slightly different process. The same reconnection happens, but you accelerate electrons. Some of those electrons are accelerated and they travel down towards the surface of the star. When they impact on the dense chromosphere, they ablate material, which is heated and rises up into the corona. Some of the electrons travel out into the interstellar medium and they produce radio emission because they're accelerated charges. So there are different ways to produce the X-ray emission. The thermal emission is largely just the background heating of the corona. The hard X-rays that Moira was talking about, greater than 10 keV, generally come from these flare-like events, where you have a population of accelerated particles. So it's not just the background thermal population.
Right. Thank you very much, Moira. So I'd like to thank you again for the very clear talk, very easy to follow. You made it very easy to follow because it's a very complex subject. And thank you a lot for sharing your research, your knowledge, and giving your time to present this talk.
It's a great pleasure, and thank you for inviting me. It's a delight to see all of you. I hope at some point in the future I'll get to see more of you in the flesh.
Yes.
But it's still a pleasure to see you online.
Yes, I also hope the next time it will be in IAG. I don't know if you have been in IAG before.
No, I don't think so.
Not yet. Okay. So hopefully in near future.
Yes.
Yeah, you should come here to Sao Paulo to give the talk.
I should.
Absolutely.
Yes. You have much better weather than we have in Scotland. Okay.
So
Okay.
Thank you, Moira.
Thank you.
Bye for now.
Thank you so
Bye-bye.
much.
Ciao.
Ciao, ciao.
Bye-bye, Moira. Bye.
Richard, we can stop the broadcast.
Okay.